Hello, I'm Davide Coppola, and I will be presenting our work interpreting mechanisms of prediction for skin cancer diagnosis using multitask learning. The presentation will follow the outline that you can see on the screen. Skin cancer, and in particular melanoma, is one of the main causes of death worldwide, yet when identified in time, the odds of survival can turn. In dermatology, the identification task is usually carried out through established rule-based methods, the main two being the ABCD rule and the 7-point checklist. Both methods are based on the recognition of specific features on the lesion and rely on the expertise of the doctor. In particular, the 7-point checklist aims at recognizing 7 attributes on the lesion, each one giving a score. The scores are thus summed together, and the diagnosis of the melanoma depends on whether the sum exceeds a predefined threshold. The last decade has seen the rise of deep learning algorithms that have permeated every field of research. They have provided amazing performances in many applications, including healthcare. In dermatology, researchers have reported systems performing better than trained doctors. Surprisingly, the real-world applications of these methods are still limited. It would seem that their main reason is the lack of trust towards these methods, as they are unintelligible black boxes for us humans. This has recently prompted an increase in the number of works in the field of explainable AI that strives to understand the reasoning and mechanisms behind those methods. With these premises, the questions arise about how it could be possible to join the accessibility of an established rule-based method with the potential offered by deep learning. Furthermore, how can we design this model in a way such that we are then able to examine what it is learning? This work tries to merge together the utility of a well-known method for melanoma diagnosis, the 7-point checklist, with deep learning. This rule-based method inherently suits a multitask learning algorithm design, as it consists in identifying specific features on a skin lesion, which can be thought of as multiple strongly related tasks. In this framework, we introduce gate elements that during training learn which feature maps to share between tasks. Gates also serve as an additional function, as they allow to easily inspect the associations between tasks that have been learned by the model and gain insights on its mechanisms. The proposed model is a convolutional neural network that, given dermoscopic images as input, learns to classify 8 different tasks simultaneously, those being the diagnosis of the lesion and the attributes of the 7-point checklist. The main architecture can be summarized as a repetition of a convolutional block and a gated block. The first is a standard sequence of convolutional layer and max pooling, where there is one for each task. The gated block is introduced in this work and is where the tasks are allowed to share features through the learnable gates. It is known that even for related tasks, not every feature learned by a certain task is necessarily useful for another. The model should learn to share only what is necessary. A gate allows to have this behavior by selectively peaking or suppressing features learned by another task. Ideally, gates would be binary switches, but this would not be learnable through standard gradient descent. For this reason, they have been modeled as vectors of continuous values, constrained in the interval from 0 to 1. A gated block consists of multiple gates, one for each task. It receives as input the task-specific feature maps extracted from the convolutional blocks and concatenates them over the feature axis to obtain a single tensor. The gates operate on this concatenated tensor by element-wise multiplication, effectively masking the features from the other tasks that the algorithm deems unnecessary. While the single values in the gates are learnable, by design, the gate values corresponding to the features of the task itself are kept constant and equal to 1. This would allow each line to have a certain degree of task specificity. The features obtained in this way are then passed on to the following convolutional blocks, and the sequence is repeated as shown in the previous slides. The model can be trained through standard optimization techniques. In particular, each task is a classification task and is associated with a focal cross-entropy loss, which adds a coefficient to give more weight to harder samples. Additionally, to tackle the label imbalance over the 8 tasks, each sample is weighted based on the amount of samples in the mini batch that have the same label. This comes from the implementation of a sampling strategy equivalent to that described by Kawahara and his collaborators in their work. This work uses the publicly available 7-point DERM dataset, which includes various data modalities for each patient, and the labels associated with the lesion diagnosis and the checklist attributes. In the experiments, only the dermoscopic images are used as input, and the data is split according to the details provided. A number of experiments have been carried out on this data, testing variations of the base architecture. Here, 3 are presented. Standard refers to the basic configuration of the model, as presented earlier. In binary, the 5 diagnosis labels have been grouped in melanoma versus all fashion to see how this would affect the model. In gates off, the gates have all been closed and set to the constant value of 0. In each of these, the model is always trained from scratch. Performance using standard metrics is summarized here for the diagnosis task and as an average of the 7 checklist attributes. This shows that the standard architecture has a better performance than the gates-off experiment, indicating that the sharing of some features among the tasks has a positive impact. The binary experiment has a better performance on the classification task, probably because the binary classification of a lesion is easier than the identification of 5 labels, as in standard. On the other hand, performance from the checklist attributes seems comparable to standard. Yet, none of the proposed experiments achieves a performance comparable to the method proposed by Kawahara, with which there is a discrete gap in the results, especially with regards to the diagnosis task. This may be due to the fact that this method uses additional data in their training pipeline, and that a pre-trained inception net on ImageNet is used as a base architecture in their proposed framework. Since the network is trained on recognizing the 7 attributes in the checklist, the classic rule can be applied to the predicted labels as a way of detecting melanoma. The diagnosis obtained through application of the rule is referred to as inferred diagnosis, in contrast with the direct diagnosis which comes from the predicted label for the diagnosis task. For the experiments, results can be compared to the ground truth, derived by the application of the rule to the true labels in the dataset. A threshold of 1 has been chosen for the presented cases. Here, both binary and standard show comparable results with the ground truth with regard to inferring melanoma. Due to the low threshold, the rule has a high sensitivity to recognizing melanoma, as shown by the high number of false positives in the confusion matrices. As previously stated, gates allow to inspect the associations learned by the network. To do this, the sharing fraction is introduced as a metric evaluating the average value of the gates between a task T, receiving the features, and a task I, giving the features. The value indicates the amount of sharing between the two tasks, where a higher value implies a stronger relationship between them. This allows to build a sharing matrix for all the gated blocks. With regard to the standard experiment, the sharing matrix obtained at the last gated block before the classification is presented here. This should contain the more abstract features identifying the classes. It can be seen how the diagnosis task is the one that relies more on the other tasks, as it presents a higher sharing value than the average in the matrix. This is an indication of the fact that the information learned through the attributes is helpful for the classification of the lesion. Particularly high values are noted with the so-called major criteria in the checklist. The matrix also shows that the model is indeed learning to be selective and not sharing everything as desired. This can be noted by some of the values close to 0 in some of the rows. To sum up, in an effort to develop methods to understand the mechanisms learned by deep learning models, in this work a new framework for multitask learning has been proposed that is based on the idea of having learnable gates that choose which features are useful to share between tasks. Looking at the values taken by the gates allows to gain insights on the relationships and mechanisms learned by the model. The application of the method to the problem of classifying skin lesions according to the 7-point checklist on the related dataset has shown a classification performance behind the state-of-the-art method. The inspection of the gates has though revealed how each task interacts with each other, and in particular how the model has learned to use the information from the auxiliary tasks for the final diagnosis. The proposed gate elements have appeared to apply selectivity as intended. This work is but a starting point towards true comprehension of the reasoning behind deep learning models. To have a greater impact, work must be done to obtain a more reliable base model. Experiments with different architectures could be tested, and additional data may be included in the pipeline. Furthermore, the simple metric presented to evaluate the associations learned by the network might be further expanded and discussed with practitioners in order to obtain more meaningful insights. Thank you for your attention, and have a good day.